Welcome, everyone, to perhaps the most critical chapter of our journey. Imagine you are trying to find a ghost in a dark room. You know it's there, but no matter how hard you stare, you can't see a thing. In our world, that room is the mass spectrometer, and the ghosts are your neutral molecules. I've seen many scientists get frustrated because their data looks like empty noise. They blame the vacuum or the software, but the real failure happens at the source. In mass spectrometry, if you don't charge it, you don't see it. Neutral molecules are invisible because they cannot be moved by the electric fields that drive the instrument. Ionization is the charge catalyst. It's like turning on an infrared light that suddenly makes the invisible visible. Today, we master the fundamental physics of the electric spark, required to turn neutral samples into actionable data. Let's start with the non-negotiable law of the lab. Mass spectrometry is the study of ions, not molecules. To move a molecule through an analyzer, we need to grab it using electric fields. But an electric field has no grip on a neutral species. Think of it like trying to move a wooden block with a magnet. It just won't happen. You have to turn that block into iron. We must bridge the energy gap between a stable neutral state and a charged ionized state. This is an energy transaction. We either force an electron out or bribe a proton to come inside. According to the Franck-Condon principle, this transition happens so fast that the nuclear distance of the molecule doesn't change. The question is, does your molecule have the ionization energy, or IE, required to make the jump? Without that startup capital, your sample remains a ghost that never reaches the detector. Don't fall into the trap that more energy is always better. Precise ionization is the goal. I categorize energy delivery into two modes. First, we have hard ionization. Think of this like throwing a fine vase against a brick wall. Techniques like electron ionization, or EI, use 70 electron volts to blast an electron off. This creates a molecular fingerprint of fragments. It's great for identification, but tough if you just want to know how much the whole ghost weighs. Second, we have soft ionization. This is a subtle negotiation. We use spray physics, like electrospray ionization, or ESI, to gently add a proton, or H+. This keeps the molecule intact. Your task is to choose. Do you need the shattered fingerprint for identification or the intact mass for quantification? Let's look at the physics under the hood. Think of the molecule's internal energy as its internal temperature. When we transfer energy to a neutral molecule, M, we are raising its temperature. If the energy exceeds the ionization energy, or IE, we get the molecular ion, M+. But if we keep pushing, we reach the appearance energy, or AE, of various fragments. This is where the structural integrity begins to break. In hard ionization, we purposely overshoot the AE to create fragments like M1+ and M2+. In soft ionization, we try to stay below the AE to keep the molecule whole. As a master, you must learn to deliver energy with the precision of a scalpel, not a sledgehammer. Why do some molecules ionize beautifully, while others act like stubborn ghosts? It comes down to proton affinity, or PA. Imagine a crowded cocktail party where some people are social magnets. In the gas phase, some molecules are proton magnets. They have a high PA, meaning they want the charge more than their neighbors. If your analyte has a high proton affinity, it will grab any available proton in the source and become an M+H+ ion. But if your solvent has a higher affinity, it will steal that charge. This is the root cause of ion suppression. It is a competitive market for protons, and as a strategist, you must ensure your analyte isn't being bankrupted by a greedy solvent molecule. Ionization isn't just a step, it's a filter. If your ionization physics is wrong, your data is a lie. If you apply hard ionization to a fragile protein, you'll see a spectrum of fragments and falsely conclude your sample was degraded. In reality, you were the one who destroyed it. Conversely, if you use ESI on a nonpolar hydrocarbon, you will see a flat baseline. The hydrocarbon is there, but it stays a neutral ghost because it has no way to grab a proton. You must look at the functional groups and the proton affinity to choose the specific catalyst that will reveal the ghost's true identity without creating a distorted image. Every electric spark involves a trade-off. High energy gives you fragmentation, the molecular fingerprint. It tells you where the arms and legs of the ghost are by providing structural identification. Low energy gives you the molecular ion, which confirms the ghost's weight and molecular formula. These are simply two different lenses for the same ghost. One shows you the total weight, the other shows you how the molecule is built. Mastering energy transfer allows you to toggle between these views to build a complete 3D picture of your sample. Don't just settle for a signal. Ask yourself, am I seeing the whole molecule or just the parts that survived the spark? Let's wrap up today's audit. We've established the foundation of the charge catalyst. Remember, the MS is blind to neutrals. Charge is the only currency accepted. Energy transfer defines your field of view, deciding between the whole vase or shattered shards. And proton affinity is the invisible hand that determines who gets the spark and who stays a ghost. In mass spec, charge is currency. Without it, your molecules are bankrupt. You are no longer just an operator, you are a strategist of the spark. But now that we have the charge, how do we use those shards to solve a mystery? In our next unit, Module 5-2, we master electron ionization and the art of structural identification. I'll see you at the source.